Welcome. Thanks for coming. We're in a different room today than the normal one. So I'm not exactly familiar with the technology of this room, but I think I hope you'll find that the material is interesting enough that you'll get it even if I mess up on some of the presentation. Welcome to the 9th annual Christmas tree lecture. Every year at about this time I try to get everybody in the holiday mood or help anyway, get people in the holiday mood by giving us a lecture about trees. One of the reasons being that trees are often associated with this time of year, and also computer science has trees as one of its central ideas, and somehow we can claim that we know more about trees than a lot of dummies do.
And you get Fibonacci numbers in Easter?
We get lots of. Why do you want Fibonacci's in Easter? For rabbits? Good idea. So everyone who works with computers knows that we can make giant steps if we understand the small concepts that we deal with all the time, and it's never. I don't think I'll ever run out of new things to say about trees. Every year I have to select between several topics that I might choose, something that I learned about trees during the year. And this year, well, I had two main ones that I chose between. I hope you like the one that I chose. Let's see, what else is there by way of introduction? Well, if I forgot something, I'll bring it in later. Now we've got this. I asked Maggie, my secretary, to have a really nice bright red poster for the book, but that means you can't read that particular slide. But we're going to try to use a combination of me opening a book here and you seeing what's on the table, and me using overheads over here instead of the way we do when we're over in our normal room. What I want to talk about today is called, can you read it there? No, chains of subsets. and this is an easy concept. Everybody knows what subsets are. And so a chain of subsets is a bunch of subsets, first subset, second subset, third subset, and so on. A sequence in which each one is contained in the ones that follow it. So that's called a chain, properly contained in it. And what I want to talk about today is something that at least half a dozen people have discovered independently over the years, and they came across the same concept in a variety of different ways, and that's always a sure clue that something important is involved in this concept. The first to discover, as far as I know, was Professor De Bruijn and two of his students, and they published it in 1951. De Bruijn was my sort of second thesis advisor. After I got my PhD, every time I had a question I couldn't solve, I used to write him a letter, and then he would write back giving me a hint on how I could get there. And other people came up with it in the 60s and the 70s and 80s, 90s, and this summer there was a brand new application of it, which I'm going to get into today. But the key explanation of why it's so simple and nice was made by Curtis Green and Dan Kleitman in the 70s. Actually, when I announced this talk, I didn't realize that they had already discovered one of the things that I had noticed earlier this year when I was looking at De Bruijn's paper. But since then, I've learned that it's an idea that comes over and over again. So the idea is we want to take all the possible sets of an n set, all the possible subsets. There's 2 to the n of them, and we want to arrange them into chains that are disjoint. So we want to put every set into one of the chains, and pretty soon you'll see what I mean. In fact, I can show you one of the. Let me try this aspect of technology here, just to show you one of the examples. So suppose we have, for example, all subsets of, whoops, wrong. Does that work? Okay, can you read that okay, I hope? I just made these slides a few minutes ago. So all subsets of 5 elements we represent by a bit string, zeros and ones, and so it's 1 if the guy's in the set and 0 if it isn't. So if you read to the right in each line, you're always adding one new element, and all 32 elements are in there in one of those lines. Okay. Now the total number of lines is 10, and well, in fact, you see. It's also grouped, so by the columns you have all the things that have all the subsets of 0 elements, 1 element, 2 elements, 3 elements, 4 and 5, and so on. So if you have 2 subsets with the same number of elements, they couldn't possibly be in the same chain. So since we have 10 elements, 10 subsets that have 2 elements in them, we got to have at least 10 chains if we're ever going to divide all of these things into chains. And you can say, well, what good is it if we can divide it into chains? And well, that's a good question. I mean, actually, we didn't used to have to answer that because we just say, well, it's beautiful, so therefore it's useful. But now we also say, well, there's lots of reasons why you might want to do it, and that's why so many people discovered it. One is, for example, if the number of elements is odd, then the number of ways to take, let's say n is equal to 2m plus 1. So then the number of ways to choose m of the elements, just a little less than half, is the same as the number of ways to choose m plus 1 of the elements, because choosing the m that you're picking is the same as choosing the m plus 1 that you're not picking. And this is the largest binomial coefficient. There's more of the cases in the middle than in any other place. Well, now it's not too hard to prove that there exists a way to map all of the choices of m things into the choices of m plus 1 things that makes a matching, so that every m set is matched to an m plus 1 set, and those, and it exhausts all. No 2 things are matched to the same one. And there was an easy way to prove that algebraically that it exists, but for a long time nobody knew any construction that would actually show, if n was if m was a million, how would you write down, saying what's the mate of the following million set? What element do you add in order to match it? And so this method that I'm going to talk about today gives a real easy answer to that problem. For every set, we're going to be able to find a natural set that it's contained in, which we can sort of match it with. Okay, so for example, here if you just look at the middle columns here, we've matched the middle elements of all combinations of 5 things. Another thing is a very famous theorem of Sperner, goes back to the 20s, and it's been applied so many times. It says if you have any collection of sets whatsoever, any collection of subsets whatsoever, and none of them is contained in any of the other ones. This is called a clutter, by the way. It's got different names. It's called an anti-chain, but it's also called a clutter. Not the greatest word to say that you spend your research working on clutters, but some people did, and they proved good theorems. So a clutter. How big can a clutter be? How many sets can you have in which none is contained in another? And the answer turns out to be easy because of if we know this chain decomposition. Because if you have any 2 elements of a clutter, they have to be in different rows. So the best we could possibly get is 10 elements in a clutter, and one way to do it is to choose one of the columns, for example. Okay, so these are some of the simplest applications of the idea, and I'll go into some more. But let me tell you what rule is that led to this pattern. That's so simple because Well, it has to do with trees. Surprise. Get myself a pen. Now, first thing that I like about trees inside a computer is that they represent matching parentheses. Anybody here ever program in Lisp? A few people know about matching parentheses. Okay, so you have left parenthesis, right parenthesis, and if you write down a bunch of parentheses at random, let me just do it. Suppose I do a right. Let me see. Actually, I haven't tried this before, but people who've heard me lecture before know that if I ever need a random example, I always go to the number pi for the example. In fact, I've been doing it so much now that in the latest printings of the Art of Computer Programming, you can look in the index and there's an index entry for pi used as a random example. It tells you all the pages in which that was done. Somehow it always seems to be something that works and makes a good unbiased example.
But not to a random base.
Not to a random base, but like if you say, what's the most interesting permutation of 4 elements? It's 3, 1, 4, 2. And almost always when you have a conjecture about permutations, if it's false, it'll fail for that one. I don't know why. Now I'm going to give you another trick that wasn't advertised in this, in case you ever have to know the value of pi in binary. Because I've never published this, but here it is. I know the octonal facts about pi. Now, what you do is you remember this little phrase and you say, most people only know pi in the decimal number system, but I know the octonal facts about pi. And you shout the word know because it means 0. But otherwise you count the number of letters. So this is 311037552. And so now we write it as 3, 1, 1 in octal, 0, 3, 7, 5, 5. I haven't worked one out in hex yet, but this is good enough. So now I'm going to write a right parenthesis for every 1 and a left parenthesis for every 0, just to get a random example of parentheses. And those of you who have some experience with Lisp will have an advantage over the rest of us, but not too much. Okay, now one thing you can do, as everyone knows with parentheses, is match them. And going back to why am I doing this, it's because this is an example of a random subset. So I'm going to find out which chain it belongs to, what are the things to its left and its right in the chain of all subsets that have that many bits. So you start out and you can group the parentheses. Okay, so here's a group. Here you can match these guys. Anytime you got a left followed by a right, you can match it, and so effectively remove it from the diagram. So then I can match larger constructions. This one will match. Maybe. Oops. Let's see. Here's one that's going to match here. This guy can come up to here. This guy over here. If I match everything, it's not going to be too interesting, but that'll be another interesting fact about pi. Okay, here we go. I think I'm done. I think everything left is unmatched. This guy is unmatched. This right parenthesis is unmatched. And this right parenthesis is unmatched. This left parenthesis is unmatched. Okay, now, in general, if I do this, then I will have found little regions of matched stuff, and then I'll have a few right parentheses maybe that are unmatched, and a few left parentheses that are unmatched. at the end. But certainly all the unmatched right parentheses have to start out. So in general, it'll have the form something like, theta 0 in a right parenthesis, and then theta 1 in a right parenthesis, and then sort of theta j, say in a right parenthesis, theta j plus 1 in a left parenthesis, and then finally we get, somehow theta sub k, where each of these thetas is a balanced thing. In this example didn't have anything that matched at the extreme left or extreme right, but that could happen. But anyway, in general, then parts of things will be unmatched, and then you'll have, j unmatched right. Parts of things will balance, and they form a unit that's a box that we don't have to look inside. And then there's these unmatched things, the right parenthesis, j of them, and left parenthesis, k minus j of them. And sometimes j is 0, sometimes k is j, but in general, it'll look like this. And what we do to find a successor is very simple. We just change this left parenthesis to a right parenthesis. Make one more, make one switch. So theta 0, everything else stays the same. But now we're going to have lefts over in the rest of it. So that's the rule that it defines a successor of every element. And in the previous slide, when I showed you all the chains for five subsets, that was the idea. The zeros and ones, you find a 0 followed by a 1, you put a box around it, effectively remove it, and then you look for another 0 followed by 1. You keep on doing that until you can't do it anymore. Then everything in the boxes is called theta something or other, and you've got a few zeros, a few ones maybe that haven't been boxed, and a few zeros that haven't been boxed. So you take the first 0 that hasn't been boxed and change it to a 1. If, however, there aren't any zeros that all the zeros have been boxed, then you're at the end of the chain. And if you want to go backwards, obviously you just change one of the right parentheses to a left parenthesis, and you keep on going until there are no right parentheses unmatched. So that's the way to move around in this diagram. So it's equivalent to many other ways of developing the same chains, but it's nice because, well, in one sense, you see every way of making of putting things into a box corresponds to a tree structure. For example, if you have parentheses that go like this, that's a set of two formulas, and the left-hand formula has another one inside it. And so so I can this binary tree, this tree represents that formula. If I had another guy over here, I could make another one. If I want to put another parenthesis in here, or two parentheses in there, then that would correspond to adding more legs to the tree. So there's a very natural way to associate parenthesis pairs as an encoding of trees. In fact, you just walk along this tree, and every time you go down, you emit a left parenthesis, and every time you go up, you emit a right parenthesis. And that gives you the sequence of left and right parentheses. So that's one connection with trees. But there's another connection which is even nicer, and that is it's an infinite family of trees that I hadn't seen before, and I think is kind of pretty. So in that, namely that that we have these chains of subsets, but they also the chains themselves form a tree. So one chain can be considered to be a child of another chain. And let me show you the family of trees and then relate that to the example. But are there any questions, first of all, on this basic rule? If I give you any set of zeros and ones, you could figure out, if it's at the end of a chain or what guy goes to its right. Yep.
Yeah, I'm a bit confused as to how the rule works. Could you show me how it works?
Yeah. How many rights do you want? Okay. So we match this guy. That's theta 0. And then this is theta 1 is empty and theta 2. So this will now go into I'm sorry, this is the end of a chain because there's no left parenthesis.
Okay.
All right, so that's 0, 1, 1, 1. All right, yeah, and I showed you these examples so you could see. These are chains on 5 elements, but if you just forget all the ones that end with 1, just forget they're there, and cross them out and drop the last guy, then you've got the rule for 4. So 0, 1, 1, 1 appears in the third last row. No, it's at the end of a chain. Yeah. Right. Okay. All right. There. Now, let me show you another construction that ties in with this, and this is something that I just learned basically this morning. So let's start to grow a family of trees, and we start out. The first tree is pretty simple. I'm going to get my cheat sheet if I can find it. Yeah. First row is pretty simple. Now, the rule to get to the next stage is it's very simple. You take every node and add a new child to it. So there's only one node, so to get to the next step, I just add a new child. Now, this might seem like a very simple rule for generating trees. In fact, it leads to binomial trees if I don't modify the rule a little bit. But it's almost the rule that I want. So here I'm going to get to the next step, I'm going to just add another child to each guy. But there's a new rule, and that is every second time I don't allow a child for the guys at the very bottom level. So here I'm only going to get 3 instead of 4. So the guy at the bottom level doesn't get a chance to sprout children. And I only use that rule half of the time. So the next time I won't use the rule, so everybody gets a new child. So I start with this, all 3 gets a new child. This guy gets a new one, this one gets a new one, this one gets a new one. But at the next step, I'm only going to allow the top 4 guys to have new children, and so I'm only going to get 10 instead of 12. So here are the 6 that I start with, and so I add 1 to this, 1 to this, 1 to that, 1 to that, and I should have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and that's the next time I'll have 20 because I don't use the special rule, and so there will be a new guy here, a new guy here, new guy here, new guy there, guy here, there, there. Here, there, there. That should be 20 if I did it right. Okay. So now, the dots in these trees represent chains in my example. So if we go to chains 5, this corresponds to the case here where I had 10 nodes in the tree because there are 10 chains. And what you do is you imagine that everything is a child of the first one above it that's bigger than it. So the guy at the top is this grand chain here. It has 4 kids. Those are the 4 kids are the 4 chains of length 4. And actually I drew this from right to left. So this is the first chain. This is the second child, and it has one below it. So this has 1 child below it. And then the other 2 children both have 2 kids, as shown here. So that's the correspondence between this family of trees and the other. So the binomial trees that have been used for lots and lots of applications and priority queues and things. Only use the first rule, saying just add a new child to everybody at each step. But here we have this extra hooker that says every second time don't. So the number of nodes you have is 1, 2, 3, 6, 10, 20, and the next time it's going to be 35 because there are 5 guys here who won't have kids. And this is equal to the middle binomial coefficient, the number of chains. So this is 5 things taken 2 at a time. This is 6 things taken 3 at a time. This is 7 things taken 3 at a time. And then we'll have 70 as 8 things taken 4 at a time, and so on. That's the number of nodes in this way of growing a bunch of trees. So here we have a rule by which we not only have chains of subsets with various applications that I'll describe, but also those chains of subsets themselves fit into a nice tree structure that has some properties that we can explore. Now, in fact, let me try to explore let me show you one thing we can do with them, and that is instead of writing them as nodes, let me write them more as so that they look a little more like chains. And so the rule then is when a chain. So here these two guys actually represent two sets. The straight line is what I call the dot on the left-hand side. Now here I'm going to have 2 straight lines because there are 2 dots over here. And what happens is each line gains an element. So the 2 becomes a 3, and also gets a new child, but the new child has 1 less element. So it turns out that this is like this, and I can draw it this way. So here's a chain of length 3 and a chain of length 1. Now, when I go to the next step, I do the same thing. I start with this chain of length 3, but I convert it to a chain of length 4, and I put a new guy underneath a chain of length 2. And this chain of length 1 becomes a chain of length 2, and that would also get a chain of length 0 underneath it, but that's why we left it out at that stage. Because
can you say that again?
Yeah. Say that again. That. Yeah, differently. Okay, so the general rule is if I have something that looks like this, it becomes at the next step, from 5 it goes to 6, and 4 underneath it, like that. So on the left-hand side, I said I had this becomes this. In other words, every node got a new kid. Here, every chain gets a new chain below it, but it grows in length by 1, and the one below it has shrunk by 1. And that's why this funny rule comes along at every other step, because the guys at the bottom have only chains of length 1 in those cases. And that's another way to give you the exact same construction that I told you about when I'm matching left and right parentheses. You can look and see what the rule is, but basically if I have more complete notation. In fact, I want to try a notation out on you guys and see what you think, because if it works, I might use it in volume 4. I always have to remove this white strip from the paper. It drives me up the wall when I see a lecture and somebody uses overheads and not remove the white strip. Now, here's the idea. Suppose that everything in the tree here has a successor that has 1 more element. Every set has a successor that has 1 more element. The successor, if you're not at the end of a chain, your successor just means move to the right in the chain. But if you are at the end of the chain, it means move up to your parent. Move up to the one who spawned you. And this gives everybody a successor except the all ones. vector. And so I could use the notation alpha goes to the right to beta, saying that this means that beta has one more element than alpha. And alpha, like this, beta, would mean that the same thing, that alpha has one less thing than beta. But there's going to be a successor. Everybody's going to have a successor that becomes one larger and predecessor. And so here's the general rule. Fleshing out what I said here in diagram, I can also write it this way. Suppose I have strings of zeros and ones, alpha 0, and alpha 0 is the parent, so it's the predecessor of alpha 1. Alpha 1 is chained to alpha 2, and then let's just give an example of a chain of length 4, alpha 3, alpha 4, and then alpha 4 goes to alpha 5, which is the parent again. So now this would be a chain of length 4 guys. Everybody has, alpha 1 has alpha 2 as successor, alpha 2 has alpha 3 has alpha 4 as successor, and their predecessors go this way. But then when you get to the end of the chain, alpha 4 has a successor that's in a different chain, alpha 5, and alpha 5 does not come back to alpha 4. Alpha 5 has its own predecessor, and similarly alpha 0. I don't know of any other notation that tech would handle that could accomplish this kind of. So if this is true, then at the next stage, what happens is that alpha 0 followed by 0 is now going to be the parent of alpha 1 followed by 0, and that's going to be chained to alpha 2 followed by 0, alpha 3 followed by 0, alpha 4 followed by 0, and alpha 4 followed by 1, and then alpha 5 followed by 1. And the alpha 0 will also be, no, I'm sorry, alpha,
Arrow.
what?
What is arrow?
Arrow, that's this upper half arrow. Okay, alpha 4 followed by 1, and this is the half right arrow. Actually, it'll look much better if tech does it. That's why I wrote software. But plan ahead. I want to write on this. I will. This will all be clear in a minute. Alpha 1, 1. Alpha 2, 1. Alpha 3, 1. And then up to here, alpha 4, 1. Now, what I meant is I had a chain before, and I had the parents of the guys at the left and right. They both hook to a chain of length 2 more. Alpha 0 is the beginning of a chain that ends at alpha 5, and that's a parent that comes to this one. Now, when I add a new bit, then I have to say what happens to the n plus 1 bit strings. So I have to say what happens to all these things when I put a 0 or a 1 after them. And the answer is the original chain stays as it is. I put zeros after it. Those are left parentheses. They aren't going to really matter in that other rule I told you about. And then I put a right parenthesis. Then I put a 1 at the end. So alpha 4, 0. So this chain used to be of length 4. Now it's of length 5. But the parent of this chain is alpha 5, 1, which is actually the end of a new chain that started with alpha 0, 0. And the and then there's another new child. This was a chain of length 4, so it's supposed to lead to a chain of length 5 and a new child, a chain of length 3. And so here's the chain of length 3 by putting 1 after the first 3 guys. And that's the construction that was used to get from 5 to 6. So here's 5, and I swear that I did this with Emacs macros. I started with this file, and then I typed in one of the most interesting Emacs keyboard macros I ever did in my life, which did this little operation, changed each line into adding zeros or ones and putting them on. And so it goes from this sequence where I have start out with something of length 6, and it becomes a length 7 followed by a length 5, and generates the set of things on six elements. Okay. What?
Is that with a regular expression, or what's the
No, just a keyboard macro. You say meta f to go to the next word, and then yes. Yeah, well, no. Well, yeah. You can do it several times at the end and make sure that then you kill it. I mean, I had to be a little tricky. I learned that trick from my wife. But try to do it in WordPerfect. I don't know. But anyway, it's another reason why Emacs is great. So now, if I had had that macro, I could have gone from chains 4 to up to chains 5 and so on, and started out with chains 1 and gotten all these things going. And I'm sure that a great Java applet will do this, et cetera, et cetera. But now, these are the chains, and that's not the end of the story. One of the next interesting things is that Paul Erdős made a conjecture that, he said Sperner's lemma. Okay, it's true. You can't have more than 10 subsets of the set of 5 elements that don't contain each other. And in general, for n, you take the middle binomial coefficient, and that bounds the maximum number of sets that you could have that don't no set containing another. But Erdős said, what if I had elements that were red and green, and I tried to find a lot of sets of these red and green ones, like maybe you have 5 red and 3 green, say. And the rule is one set can contain another set, but the difference between the two sets has to involve both red and green. So I can't get from one set to another by adding a bunch of reds. I can't get from one set to another by adding a bunch of greens. But if I add a mixture of the two, that's okay. So could I get more sets then? I'm allowing two sets to one set to contain another, as long as the difference between the larger and the smaller isn't the pure color. Okay. And Erdős said he didn't think that would give you any more flexibility, that you still couldn't get more than the middle binomial coefficient in the number. And that conjecture was proved by Katona, but it also comes out very nicely out of this chains of subsets thing. And I want to explain that to you quickly without giving the whole proof. Let's suppose, for example, that there are 5 red ones and three green ones. That's Christmas colors. So I'll get you a picture of chains 3. What we do is we arrange the red elements in chains and the green elements in chains, but we consider this sort of a cross product of the two. So I can now get a bunch of so all the subsets of 8 elements, all these 2 to the 8th ways of doing it, I can actually think of like this. I have okay, there's the 3 elements, has a chain of length 4, and it has also chains of length 2. I'm going to write those vertically instead of horizontally. But now I'm going to also look at the 5 elements, the 5 red elements, and there are chains of length 6. So there's 1, 2, 3, 4, 5, 6, and I can make this kind of a grid here. And then there's other chain of length 4 here. So here's 4 by 4, and then the next one is another 4 by 4. And I don't have time to draw this whole thing out, but here's a 4 by 2. And so in general, I could here I'd have a 2 by 6, and 2 by 4, and a 2 by 4, and a 2 by 2, and so I get these rectangles. And the rule is, so for now I've divided all the possible subsets into these rectangles, right? Because I figure out which chain, which red chain the set belongs to, and which green chain the set belongs to, and that gives me one of these. The red chain times the green chain. If the red chain has length 4 and the green chain has length 6, then I get 24 elements that belong to those respective chains. And so now what's the rule? The rule is that I'm not allowed to have two sets from the same row or column of any one of these rectangles. So in this first rectangle, I could have at most 4 elements. I could choose one out of each row, but I can't choose any 2 in the same column or anything. And here 4, 4. Here's 2, 4. And in general, if you've got a K by L rectangle, you take the minimum of K and L, and that's as many sets as you could have. Okay. So now what you do is you add up the sum over all these rectangles of the minimum times, just add up all the minimums. So here I'd be 4 plus 4 plus 4 plus 2 plus 4 and so on. And this would be 2 plus 2 plus 2 plus 2 plus 2. And add that all up. And lo and behold, that gives you exactly the middle binomial coefficient. And this was stated by Green and Kleitman in their paper without proof. In fact, they just seemed to think it was obvious. And I'm going to write to Curtis Green tonight and say, well, can you please tell me why it was obvious? It took me, first of all, I checked it with Mathematica to make sure that I wouldn't have to waste time, and sure enough, it was true for M and N up to 10, and so then I said, okay, I better prove it, and there is a fairly nice proof, but I don't know an easy proof of that, but it's true. One thing we can do though pretty easily is figure out what these numbers are, how many chains there are of each length. So that I claim is a fairly easy question. For example, here are our chains on 5 elements. How many chains are there of length 6? Well, you see, we know the total number has to be the binomial coefficients at the bottom. So this is going to have to be 1, 5, 10, 10, 5, 1. So the number of chains of length 6, so if I take the difference here, I get 1, 4, 5, 0. Well, these will just be the negatives. But so there's got to be just one chain of length 6 and 4 chains of length 4, and 5 chains of length 2. It's the only way that can work out. So the answer is the number of chains of length k is something like m choose n minus k over 2 minus the previous binomial coefficient. Because these are the difference between two consecutive binomial coefficients. Okay, is this clear? You have some questions?
Is it equal or is it less than?
It's equal. This is this number. In other words, let me give you the binomial coefficients for 8. Is 8 choose 2 is 28. 8 choose 3 is 56, isn't it? 8 choose 3 7 times 8 choose 3. 8 times 7 times 6 over 6. Yeah, 8 times 7 is 56, and then 8 choose 4 is 70, as we said. So it'll say that when I divide all the subsets of 8 elements into chains, I'm going to have one chain of length 9, 7 chains of length 7, 20 chains of length 5, 28 chains of length 3, and 14 chains of length 1. And that's going to do it. And now what you do is you take these numbers for m, and you take the similar numbers for n, and you multiply by the minute. So this tells you the number of k by l rectangles you have, and you multiply so it's something like the summation of ak, al, minimum of k and l, and that turns out to be equal to m plus n. Choose m plus n over 2, the middle binomial coefficient. And I would love to see a really simple proof of this fact, because the A's are equal to the difference between, A sub 1 is things that are very near the middle, and A sub 2 is the difference of two binomial coefficients just after that, and so on. K and L have to be K has to be congruent to 1 mod m. If m is even, then K has to be odd, and if m is odd, then K has to be even. All these chains, the chain lengths are either all even or all odd, depending on whether m is odd or even. So that's there are other numerical things that check out when you study this. For example, if you take the power series C of z equals z plus z cubed plus 2z fifth plus 5z seventh, and you can keep on going. These are the number of trees, of binary of trees, 1, 1, 2, 5, 14. It's one of my favorite sequences. And C of z, and so you can use this generating function, and you can figure out how many chains there are of a given length, because it's the number of ways to make balanced formulas that you're going to leave free parentheses next to. So, for example, C of z to the fifth, it turns out that C of z to the fifth, if I looked at the coefficient of z to the 2n plus 1 in C of z to the fifth, it had to be equal to, I think it was 2n over n minus 2 minus 2n over n minus 3. This turned out it had to be true because I knew how many chains there were that had five balanced formulas to be inserted in them, and so I thought, okay, maybe this is a new formula to teach me something more about this function C of z. But it wasn't too hard to derive that from other formulas I already knew. So anyway, it did check out, of course. Now, let me show you the brand new thing which came out this summer. And here I don't remember if it was Bill or Bob, but anyway, you can shift now to the overhead camera, and I'll show you that paper that I just downloaded. I press this off. Maybe I press it a little harder. Yeah. Can we see the? Show this paper. So the paper by Jerry Griggs, Chip Killian, and Carla Savage, I downloaded from Carla's website, and it says Venn diagrams and symmetric chain decompositions in the Boolean lattice. So they found some of the things I've already told you were things I learned by reading this paper. This idea of having all the chains put into a tree, and they use this to make Venn diagrams. Now, have you people know what Venn diagrams are? This is something that you learn in high school, or at least you used to. So it's a set of curves, and so you have three curves maybe, and then if you look at the things that lie inside of two of the curves, A and B, but not in C, that gives you one subset of the set A, B, C. And you're supposed to be able to see all the subsets by looking at different regions where the curves intersect. And there's also, if you go to the web and ask for Google, let's see, where is my? Didn't I bring that? Oh, that's a shame. I had some beautiful pictures. Okay, well, I don't seem to have brought that. Maybe I have one. Okay, it's sitting in my office. Too bad. Well, type into Google symmetric Venn diagrams, and it refers you to a page in which there's some glorious pictures of Venn diagrams that have lots of interesting symmetry. And one of the questions that was open was is there a symmetric Venn diagram for all prime n? Where it's symmetric in the sense that you divide, if you rotate by 1 over nth of the 1 over nth of a circle, then it repeats. The pattern repeats again. And people had like Branko Grunbaum once published saying that he didn't think you could do it for n equals 7, and then 10 years later he found an example for n equals 7, and then now there's complete list of them. There's 6 or 7 ways to do it, and they're quite pretty pictures. And that's one of the applications, in a way, of mathematics, is where if you have a nice picture to put on the wall. In this paper, they show how you can do this for any prime n. You can use these ideas about chain decompositions to form Venn diagrams. I'm just going to show you a simpler thing that relates to what I've been saying before, because it's cute too, and it's the basic idea. Once you get this basic idea, then you're ready to see the other construction, which is very similar. So what relation could there be between chains of subsets and Venn diagrams? Well, one thing, of course, is that we know that every subset has to be one of the regions of the Venn diagram. So what we want to do is make a Venn diagram out of what we had before. And so I will try this and see if I get it right. And so let me look for, but let me just do it with chains on 4 things, because that won't take so long. So back to the overhead, and I got to get the chains 4. Oh boy, this is not easy to see. Okay, now I'm going to take a blank slide, if I can find one, and I'm going to try to draw some curves so that you'll see that this would be a Venn diagram, that this will lead to a Venn diagram, so that there will be, so that these 4-bit codes here are going to be the regions, the areas inside the diagram. Maybe I won't have enough room on this page to do it, but with luck it'll work. But maybe I should have made a bigger example. If so, I can just recopy the darn thing. Let me recopy it, because then I know I'll have room. So 0, 0, 0, 0, 1. So here, this basic chain is the easy case where there's no balanced, no parentheses canceling at all. Then there's the 0, 0, 0, 1, 1, 0, 0, 1. I can see it better on the hard copy. 1, 1, 0, 1, 0, 0, 1, 0. I should be 1, 0, 1, 0. Okay, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1. So now the first step is we draw the lines to predecessor and successor, which means that each chain we draw a line here, and then also to the parent. So it's the closest person of size 1 less at the edge of these chains. So these are the lines that connect everything. And this is, as we said before, this is a tree. This is the tree we were talking about a few minutes ago. Now, this diagram has as many regions as there are chains. And I'm just going to put a circle here to mark the middle of a region. I should have probably put that on another sheet of paper, but it's too late now. Let me at least get another color pen. Pens. Okay. Let's see. Christmas red and green. Okay. Here's now. what I'm going to do is I want to draw lines between these dots here, and those lines are going to be curved in a Venn diagram, and the curves are going to intersect only at these dots. And so let me draw you the curve that's based on element number 4. Everywhere there's one of these little lines saying we've added element number 4, I want to cross that line. So I'm going to go from here to there. Where else do I go? Do I add element number 4? Right here. So there will be a line from here to here. Now, there's got to be somebody else in the middle here where number 4 is added, so it's here. So if I just look for every edge where 4 is the guy who is new. Here's 3 to 4, so here's a case. So I'll want to connect this one. Here 4 gets in, so I want to connect there. So I'll connect from the dot to the middle of the edge whenever the edge adds number 4. Here's one, and where else? One of these has to add a 4. This is 3 here. And I'm almost done, right? This guy to here, and this guy to here. And then this one also comes out to there. Okay, so that's a region that everything on one side of the region has a 4 in it, and everything on the other side doesn't. I do that for 3, 2, and 1 the same way, and I get a Venn diagram. So that's the idea here. So these chains of subsets also lead to Venn diagram. Yeah. I'm missing something.
In the middle.
Oh, the counterexample. What? Here? No, here. This guy. Yeah. Yeah. You also have to do it right. But if you do it right, it's supposed to work. And the lines will only cross at these circle points, because you just draw. The circle point it's in the middle of a polygon, and so you just draw that to the middle of the edges, and those lines don't cross each other. So there will be intersections though at the circle points. That's the construction, and that works. It gives Venn diagrams out of these chain decompositions. Any question on that? Okay, now I want to show you one more application, and then open up for questions. This one goes back into volume 3. Wait, well, actually, I got more. No, I got more. Oh, yeah. Now, before I do this, let me tell you something that I find even more exciting. So that is now I got this chain decomposition, but now I can associate it with permutations. Of course. And so let's look at permutations, and compare the permutation with chains. Now, where's chains 5? Somewhere. Well, the rule connecting them is simple, but it'd be nice if I could show them on the same screen. Chains 5. This looks good. Okay, so I got these chains that we've been talking about. Now I also, for every subset, I can encode it by a permutation by first numbering the ones and then number the zeros. And so for example, here's my 10010. So I call this 1, 2, 3, 4, 5. The 2 1s are called 1 and 2, and the 3 zeros are called 3, 4, 5, and that gives you this permutation 1, 3, 4, 2, 5, which is 1, 3, 4, 2, 5.
So these are permutations decomposable into 2 runs.
1, 3, 4, 10010. Where was 10010? Here. That was the third guy down. Yeah, 1, 3, 4, 2, 5. All right, you with me? So these are the permutations that have two readings. In the first line you lose because there's no way to distinguish. They all go into 1, 2, 3, 4, 5. But everywhere else, these are permutations that need two readings. You can go across and then again, and then you get the numbers 1 up to n. And the number of permutations with two readings is the so-called Eulerian number, n Euleri 1, which is 2 to the n minus n plus 1. It's exactly the number of elements that are not in the first row of the chain. So the number of permutations is right. It's the number of permutations that are, it's equal to the number of subsets like this, and we can encode the permutation this way. Now the curious thing about this is that if you go into the art of computer programming and you look at the beginning of chapter 3 where it talks about Shenstead's construction and Young tableaus, and there's a beautiful theory about inserting elements of a permutation systematically and forming two so-called Young tableaus, which are arrangements in rows and columns where it's increasing both directions, both in rows and both in columns. And every permutation corresponds to a pair of Young tableaus of the same shape. And the nice thing is that, once again, this whole method of chains of subsets has a beautiful explanation in terms of the Shenstead's algorithm in Young tableaus, because it turns out that you get two Young tableaus, so-called P and Q, when you're using Shenstead's algorithm, and each of the permutations in a row has the same Q value. So this is the, in other words, you can encode, and I drew the Young tableau here. So 1, 2, 3, 4 in the first row and 5 in the second row. That's a Young tableau. Here's another Young tableau. You see, rows and columns are increasing order, and the same thing works, of course, for permutations on the 6-element sets, and there it gets more interesting. So I put it up on the screen if I can find it. So here's the example for the 6s. So a lot of more different kinds of Young tableaus occur, and the let's see, what time is it now? Do I have time to illustrate this? 5:15. Okay, yeah. Well, I plan to run over about only 15 minutes, so I thought I would. So I can show you this. I can show you Shenstead's algorithm and what I'm talking about. Here's the idea. Another sheet of paper out, and suppose we. And it's a method that works with any permutation, but in this case, permutations are a bit simpler because they have only two readings to them. But I do think my black pen was working better than the red pen, so I'll try to find a black pen again. Boy, this light really makes me blind. Okay, let's take a larger permutation because it'll show the real pattern. It'll show what's really going on. Although it might be too complicated, I don't think so. So let me take an example. It won't be as bad as that pi example, but let's take. Suppose I had 0, 0, 1, 0, 1, 1, 0. I'll put this a little lower than 0, 1, 0, 0, 0, 1, 0, 1. Now, what I put these lower because these things get boxed. The 0 matches a 1. Left parenthesis matches the right parenthesis, and so these are the free elements underneath. So when I encode this as a permutation, I'll number the ones first. Let me take another one. I'll change this to a 1. It's the same. So now it's not going to matter in some ways what happens to Shenstead's algorithm. But so now the permutation that I get from this, I number the ones first. So I get 1, 2, 3, 4, 5, 6, 7. Then I number the zeros, and I get 8, 9, 10, 11, 12, 13, 14, 15. Now, okay, let's play Shenstead's algorithm. The idea is you insert into a tableau one step at a time. This is P, Q over here. P, and so I put 8 in P, and the first step is never very interesting because you just put the first element in, and you write a 1 here. Now the next step, 9. 9 is bigger than 8, so I put it in the first row. The Shenstead's algorithm, we prefer to put it in the first row if we can. And now, since I filled that thing, I want to keep Q the same shape as P, so I put number 2 there. Now along comes a 1, and I want to put 1 in the first row, but it won't fit at the end, so I put it where it fits, and I bump the 8 down to the second row. So now Q gets a 3 here. Then 10 is next, and so 4 comes here. 2 comes next, and the 2 is going to bump the 9 down and make a 5. 3 is next, that bumps the 10. 4 fits fine in the first row. 11, no problem. 5 is going to bump the 11 down. Here. 12 fits here. 13 and 14, so that's 10, 11, 12. Whoops. Down, I head down. 10, 11, 12, 13, and 14. And then 6 is going to bump 12. So 13 here. And 15 will fit okay, so pretend you can see a 14 there. And then 7 bumps 13 down here. So what happened is that the P array is this: 1, 2, 3, 4, 5, 6, 7, 14, 15, 8, 9, 10, 11, 12, 13. The Q array is 1, 2, 4, 7, 8, 7. I claim that if you change this, if this is 0, 0, 0 or 1, 0, 0, 1, 1, 0, 1, 1, 1, and you do the same thing, the Q array stays the same. And that's the identifier. So everything in the same row, everything that belongs to the same chain of subsets corresponds to a permutation that Shenstead's algorithm takes into the same Q. And one consequence of this, according to a theorem that I proved 30 years ago now, is that is very curious, and that is that you take any pattern of zeros and ones, and any pi. But I know the octonal facts about pi. So something like this, and now you change, and let's see, it's 0, 1, 0 goes to 1, 0, 0. I might have this wrong. I might have to put the 0 on the left, or 1, 0, 1 can interchange with 1, 1, 0. You allow yourself to move, to interchange the zeros and ones in this pattern, but only if the guy on your left on your right is a 0, or the guy on your left is a 1. Or I might have the parity wrong on that. It might be the other way around. But anyway, you consider all the strings that you can get from this one just by repeatedly doing these two switches. And the theorem says that these are exactly the subsets with this many elements that belong to chains of the same length. So this pi belongs to a chain of length 4, and you look at all the chains of length 4, and you look at all the things in the column that has this many 1 bits in it. Those are exactly the strings that you can get by interchanging these, making these local interchanges. It's a curious result. I don't know if there's any use of it, but it's true, and so you never know. Now, a question on that? Okay. Now the last thing was there's a connection to information retrieval. Right near the end of volume 3, where it talks about retrieval of with many attributes, there's a formula here which we might be able to zoom in on just to tell you about. It's an idea that it's been around for 30 years, saying by adding some redundancy to the way you store things in a database, you can make sure that the answers to all queries you want will appear consecutively in the file, and that you can get to them. And on this page here, there's a formula. I guess we can't zoom in on it, but there's formula 8 on page 567, which says that if you had 4 attributes A, B, C, and D, you could store them A, B, C, D, B, C, D, A, B, D, A, C, C, A, D, B, C, D. There's 6 permutations that you could store the attributes according to those, and then have an inverted index so that you could look up and find out everything. Well, it turns out if you do this, then any combination of 1, 2, 3, or 4 of the attributes, and no matter what you say, I want to find all cases, with where A is equal to 3 and B is equal to, A is equal to 3 and C is equal to 7. Those will all appear consecutively in one of these 6 lists. And this decomposition into chains of subsets is really a method that tells you how to do this in general for general number of attributes, and you can leave out the short chains if you're only interested in a small number of attributes. So that's one of the other applications of this idea, which I hope now you will find another application of sometime, so that you didn't waste this hour. Any other questions? Yep.
Is there some type of uniqueness to that decomposition?
No. It's very. There's a huge number of ways to make these decompositions. In fact, the way they do their symmetrical ones for the case of primes, they want to have other properties, so that if you shift everything to the right one, you stay. Then your chain also corresponds to another shifted chain, the number of ways to do the decomposition is huge. The main point of this is that it's easy to compute. It's really. I doubt if there's any easier way to decide. For example, just to find a matching between the two middle the sets of things that are n-1 over 2 elements with the sets that are n+1 over 2 elements, to find a matching between those. It looked like very hard to find any explicit rule that would do that, and this is by far the simplest rule that anybody knows. But the number of such matchings is probably enormous. There's always a big difference between what exists and what can be computed fast and really known. We know that irreducible, that primitive polynomials exist to generate finite fields of all n, but nobody knows an algorithm to compute one for given n. You just do trial and error until you find one that turns out to be primitive. Yep.
I'd just like to verify that the Venn diagram you just described as an algorithm for drawing in 2 dimensions.
Yes.
A Venn diagram is an arbitrary number of normal.
Yes. What? Does it look beautiful? I wish I could say yes, but it just looks kind of computery to me. That web page that I told you about, symmetric Venn diagrams, is a beautiful survey of everything known about it. And there's still no really beautiful one for n equals 11 yet, for example, to look at. They've constructed them that are symmetrical, but they aren't what they call simple. And the ones that are really nice. One of the reasons that these people started looking at it is a kind of a notorious conjecture that says that not only is there a matching between these two sets of size n minus 1 and n plus 1 when you have two n plus 1 elements and you're trying to match the n sets with the n plus 1 sets. There's just as many n sets as there are n plus 1 sets, and now this shows a matching, but there's also almost certainly a Hamiltonian path through them, where two matchings that together make a cycle. So you can go from n to n plus 1 to n 1, and you hit everything exactly once. And I was going to show you this beautiful picture n equals 7, where you can just see them all in this nice picture, and you can just go from all the 3 sets to the 4 sets and to 3 and 4 and back and forth, and there they are. It's gorgeous, but people have shown that these Hamiltonian circuits exist. In fact, there are zillions of them, up to n equals 23 or 25 has been computed, and there's no problem finding one. It's just to prove that they exist seems to be impossible, as far as anybody knows. It's just something like the Goldbach conjecture, where Goldbach conjecture is almost certainly true because it's true, because it couldn't be false. But there's no proof for it. The Goldbach conjecture says if you have an even number, you can write it as a sum of 2 odd primes or 2 primes, and the number of ways to do that is huge. And so nobody believes that there could possibly be a large n for which all of the primes and n minus the prime, for n minus prime would just happen to not be prime for all cases of all primes less than n. It's just it's inconceivable. The probability of that is incredibly small, and the number of solutions is huge. But to actually prove that there isn't such a funny n may be one of those problems that has no proof. Just happens to be true. Yep. Well, this was used in some IBM software. The guy Vincent Lum, who invented it, was at San Jose lab. I don't know, how many people use it. Much more. You don't need large n for this, or else the amount of replication gets huge. But it's still it's one of the tricks that lets you think of, and then you can approximate this and get something that's pretty good. By starting with this total solution, get something that has a little bit of redundancy, but you have to look in several lists instead of one. The main idea, though, is that I hope you get a little more insight into interesting families of trees and how matching parenthesis might even have something to do with completely other things, other parts of basic computer science ideas than you ever thought of before. So thanks a lot. Merry Christmas.